Here's another non-symmetric game. It's going to be a prisoner dilemma that we're going to attempt to solve with the Grimm strategy. So, first step, distill the information given into this strategic form. You identify the players, Nintendo, and Sega, and the choices that they make. I give you the unit cost up here, and then here's the choices, 250 and 350 for Nintendo, and 40 and 50 for Sega. Those are the two choices. And then depending on prices, I tell you the demands, and these are in millions. It's going to turn out when we compute profits, they're going to be big numbers in millions, and so this profit table is going to be, the numbers will each be millions of dollars. Now, this game continues each month, and that's, since it continues periodically, not just a one-time thing, that's where the Grimm strategy becomes available. Now I give you the monthly market interest rate, 0.2%. If you write that as a decimal, it is 0.002. And all demands are considered to last indefinitely. So this game continues from month to month or period to period with probability 1. Are the two goods gross substitutes or gross complements? Well, let's see. They start off with prices 250 and 40, then the demand for our demands are 1 and 2. But if it's 250 and 50, so that the price of good 2 goes up, then the demand for good 1 goes down. When a higher price for good 2 makes a lower demand for good 1, then these goods are gross complements. Now, here is the market rate, 0.002, the 0.2%, and it's with probability 1 that the game continues. That means that the effective rate is the same as the market rate. So this is going to be the effective interest rate that we're going to be using toward the end of the problem. Now, fill out this strategic form. Just take one of the cells. For example, if player 1 chooses 250 and player 2 chooses 50, then, let's see, 250 and 50, look that up here, 250 and 50, then the demands are 0.8 and 1.6. This is all in millions. Profits for firm 1 would be unit profit, so that's price minus the cost of 50. So this is unit price, price minus average cost. Then multiply that by the 0.8, and you get this number here. This is 160 million, but let's just write it as 160. And then for firm 2, we have the firm charging a price of 50, and their cost of production is 10 in the problem. So their unit profit is 40. Multiply that by the demand of 1.6. 40 times 1.6 is 64. So put that in there. And you might want to pause the video and for yourself calculate each of these other cells. Now, in the one-shot game, where these firms just consider themselves each period, what should I do? I'm not going to pay attention to the past. I won't pay attention to the future. I'm just going to play each period as if it's the only period. That's actually a foolish thing to do, but what if they acted like that? Well, the row chooser, so player 1, will notice better. This row is dominant. For the column player, player 2, better. This column is dominant. So they end up choosing this combination. Now, that's where they would end up if every period they considered that the only period. They'll end up here. They notice that there's a better payoff up here, and this is the prisoner dilemma that they have to try to resolve, that they want to try to resolve. And how would they resolve it? So try the Grimm strategy. The Grimm strategy has you cooperating as long as the other player cooperates. But if they ever cheat you, then you punish them eternally as much as you can. How would player 1 punish player 2? Well, player 1 can only choose one of these two rows. If he chooses this one, player 2 will make the best of his punishment and get 64. If he chooses this one, player 2 would get a 48. Your objective in punishing the other person is to make their life as miserable as possible. So when choosing between the 64 for him and the 48 for him, you make the 48. So player 1 would punish with a 350. Now, if player 2 instead is the one punishing, chooses either this column or this one, player 1 makes the best of it. If this is the column, he'll get a 210. If this is the column, he'll get a 180. Player 2 will choose the column that makes player 1 as miserable as possible, and so he'll get this 180. Remember those numbers. So, can they cooperate if they follow the Grimm strategy? Well, what would happen if player 1 follows his Grimm strategy, he cooperates, but player 2 cheats? Well, the agreement was to be here. If player 2 cheats, he can switch his column, be dishonest and switch his column, and he would increase his payoffs from 60 to 64. That's an increase of 4. But now comes his punishment. To punish player 2's cheating in the future period and in all future periods, Nintendo is now going to pick its second row, and then the column person is going to have to make the best of his punishment. This 48 is better than the 42, so now he's going to get a 48 rather than the 60 he would have had he continued to cooperate. So in the punishment phase, player 2 would be losing 12. The present value of that you get by dividing by the effective interest rate. In this particular problem, it would work out to $6,000. So by cheating, player 2 would gain 4, but then lose 6,000. He would not cheat. He doesn't. It's not because he's an honest person by nature. It's just circumstances do not tempt him to cheat. So now let's see if player 1 would cheat on the agreement to follow a Grimm strategy. Well, the Grimm strategy has you up here. Player 1, if he cheated, he could switch his row and get 210 instead of 200. So by cheating, player 1 could gain an extra 10. But then comes his punishment. Player 2, as we already discussed, would punish by choosing the second column. Player 1 makes the best of it and now gets 180 instead of the 200 he would have had he continued to cooperate. So that is a loss of 20. In present value, divide by the effective interest rate, and you would get 10,000. So what we have is player 1, if he cheats, he would gain 10, but lose 10,000. He would not cheat, and so he can be trusted. Not because he's an honest person by nature or he has integrity, but because it just doesn't pay. Crime did not pay for either of these two, and they didn't commit the crime. And in that way, because neither of them would cheat on the Grimm strategy, it becomes a Nash equilibrium. So actually, the Grimm strategy is a Nash equilibrium because they both do not cheat.